So looking at this momentum from a bit of a different perspective, when we go back to that bobsleigh example from the beginning of this section, the momentum is dependent on the speed and the mass. So initially, when that bobsled is at rest, it has no speed, so its momentum would also be zero. But as time goes on and the pilot and the other three members of the bobsled crew push it, they increase its speed, therefore increasing its momentum. Now, the amount that they can push on that is actually the force that they can apply to the bobsled. Assuming that they can apply the same amount of force constantly, the other thing that's dependent on the final momentum of that bobsled is the time. So really, momentum is not just dependent on the speed and the mass. It's also dependent on the amount of force that the object is pushed with and the amount of time. So in this case, we're going to call this delta P, which is the change in momentum, and that's also called the impulse. So the momentum is how much momentum the object has. The impulse is the change in the momentum. Sometimes those two terms do get used interchangeably, but it also, the impulse equals F times delta T. So we do pull in some mechanics from Unit 2 with force. Another way that you will see this equation, and it sometimes be useful to do it this way, is that mv equals F delta T, just depending on the application of the question. Sometimes it's useful, sometimes it's not, but it is another way you will see it. So here we have a baseball. Mass is 0.152 kilograms, traveling horizontally at 37.5 meters per second east. I'm assuming it would be thrown out of a pitcher's hand. Collides with a baseball bat, which lasts for 1.15 milliseconds. And immediately after the collision, the baseball is going horizontally at 49.5 meters per second west. So we'll assume that this batter actually got a good hit on the ball. So to determine the initial momentum of the ball, this is at the beginning when the ball is traveling east. So we know the mass. That is not going to change throughout this entire process. But now we need to look at which velocity matters, and that would be where it is traveling east. And momentum is what we're trying to find here. Same equation as we have been using. P equals mv. Substitute in mass 0.152 kg, v 37.5 meters per second. Multiply that out, going to 3 sig figs. Get 5.70, and the unit for momentum, kilogram meters per second. It is a vector, so when we have a direction to attach, we need to do that. This would be east. Continuing on, what's the average force applied by the bat to the baseball? Well, what we know is that the impulse, or the change in momentum, equals force times time. But the key thing here is that this is delta P. This is the change in momentum. We can't just go simply on the initial momentum. So we do actually need to find the final momentum after this ball has hit off the bat, because the force applied is from the bat to the ball. So we need to know what happened before, which we found in A. We need to know what happens after, which we're going to find now. So for final momentum, the mass hasn't changed, still 0.152 kilograms. The velocity of this ball now is 49.5 meters per second, but it is west. And we don't know the momentum at this point. Do the calculation here just because I'm going to need the space in the middle in a minute. P equals mv. So 0.152 kgs times 49.5 meters per second. Again, going to 3 sig figs, we'll get 7.52 kilogram meters per second west. Now, the change in momentum which is actually impulse. We can't use the formula of delta P equals F delta T yet because we need to figure out the actual change in momentum. Since we're being asked to find the average force means we need to know the impulse. But for the change in any quantity, it is always the final minus the initial. So the final momentum, 7.52 kilogram meters per second west. I'm just going to change that line a bit because I won't fit it all in otherwise. Minus the initial momentum, which we found in A, of 5.70 kilogram meters per second east. Now the directions here are incredibly important. We can't just subtract these two because they're not in the same direction. So we can either make them both west or both east. Likely be easier to make them both west. So we won't need to change the final momentum, but we will need to change the initial. It would be negative 5.70 kilogram meters per second west. But we subtract negative 5.70, so it would end up changing to plus 5.70. I apologize for the squishiness of that, but we have 7.52 kilogram meters per second west plus 5.70 kilogram meters per second west, which would give us 13.22 kilogram meters per second west. So now that we know the change in momentum, we know the impulse, we can find the average force. The only other thing we need is the time. And what we were told in the question is that the time that the bat was in contact with the ball was 1.15 milliseconds. Well, for any calculations, we do need the time in seconds, and there are 1,000 milliseconds in a second. So we'll divide by that by 1,000, 0.00115 seconds. And now we can go and use the impulse equation. So delta P, 13.22 kilogram meters per second west. F, we don't know. Time, 0.00115 seconds. Divide both sides by 0.00115. We will take this to 3 sig figs, and we get 11,500. We're talking about force, and force is measured in newtons. And since we do have a direction and force is a vector, this would be 11,500 newtons west.